All right, so last time we used the superposition principle, and then we still use the generalized to integral, and then we calculate the electric field created by a ring, uniform charged ring. Right? We found out the electric field, and then that's actually easier than the rod, okay? Because at the end, when you pull all the constants outside the integral, you get nothing there, okay? You just integrate the charge. You just get the total charge. Or if you want to use write this dq in terms of the charge density, linear charge density times dl, you take out this linear charge density, you just integrate this dl, you get the total length. Either way, you will get the electric field created by this ring, right? And then, as I said, you can use that conclusion to derive the electric field created by a disk, which we didn't, okay? Because that's not something I want you to know, okay? But for the rod and ring, you definitely know how to derive that, okay? Or anything like them. So for the disk, I just presented the conclusion, right? So the trick is this: you think of the ring, the disk, as an infinite number of rings with different radii. Okay. Then you go ahead and use the conclusion we drew for the ring, and then you make the radius as the variable. You're gonna have a function. You're gonna derive a function for the r, and then integrate that with the dr. You're gonna then you can get the conclusion. Okay. So, but anyway, the conclusion we presented last time, and we said that if the disk is very large, right, it's gonna become the very simple conclusion, that surface charge density, right? If the disk is this, and then the r is much bigger than the d, the electric field, net electric field, is just going to be almost sigma e over 2 epsilon naught. Right? Very easy, very simple conclusion. And the electric field, of course, it's going to be if it's positive disk, away from the disk, negative toward the disk, right? And then if you put two disks together, and then make sure that the distance between them is very small, much smaller than the size of each disk. Then for each disk, you're just going to get the same electric field, right? So you charge them with opposite charges, but the same amount, right? And then you put them very close. So this is positive Q. They have the same size, charge them with the same amount of charge of this size. The electric field between them, it's going to add, right? Because each I'm only interested in the electric field between them, not outside, okay? This guy creates the electric field in that direction, and this is negative place, so it also creates the electric field in that direction. So E1, E2, they can add, and if you make sure that they have the same amount of charge, so they will have the same charge density, right? So at the end, the electric field between them, it's just going to be sigma E over epsilon naught, right? Because you add them together. And then sigma E is going to be Q over A. And that's going to be the same for each plate, right? Because I made sure that they have carried the same amount of charge, they have the same size. So, and this is going to be generalized for, it doesn't have to be disks, right? Any plate, okay? Rectangle or disk, or just like irregular shaped. You put them, you charge them with opposite charges, the same amount, put them together very close, make sure they satisfy this condition. Then the electric field between them is going to be always very uniform with this, the magnitude, the surface charge density divided by epsilon naught. And that is how, as I said, create uniform electric field in real life. Because once we create the uniform electric field, I can use that to study the behavior of elementary particles. Right? Okay, and then by making a uniform electric field, okay, I make my life easier. I get rid of the complexity of the electric field. I can focus on the forces and the motions of these elementary particles, right? Okay, so that's what we did last. Now let's take a look at an example. So so this equation is going to be given on the test. You don't need to worry about this equation, right? This is the equation for parallel plate capacitor. We call them parallel plate capacitors, okay? So let's see how we can, we just want to practice this conclusion for parallel plate capacitors with this question, slide 13, the same PowerPoint 3. So 1 centimeter times 2 centimeters rectangle electrodes. As I said, it doesn't have to be disks, right? As long as they're big and then the distance between them is small. This is always true, okay? 1 millimeter apart, okay? 1 millimeter is much smaller than like their size, right? 1 centimeter and 2 centimeters. How many electrons must be removed, moved from one electrode to the other to create a uniform electric field? Okay, 2 times 10 to the 6 newtons per coulomb. Okay, so the problem actually tells you that I want to create an electric field, okay, using 2 rectangle electrodes, okay? So like this. Okay, so this plate has been charged positively and then the other one charged negatively, but they carry the same amount of charge, right? So the electric field between them is going to be very uniform from positive to negative, right? And we can use this electric field to study the behavior of elementary particles, which we're going to see in a little bit. Now, okay, the problem says that I want to create an electric field, 2 times 10 to the 6 newtons per coulomb. So we can rearrange this equation to find the sigma E on each plate, and then find the charge, amount of charge on each plate, right? And then the problem says that how many electrons must be moved to one electrode to the other, right? How do we get them charged? Okay, one way is this. You just remove electrons from this plate to the other one, right? You move one electron from this one to the other one, this guy is going to become positively charged. This guy is going to become negative charge and the same amount of charge, right? You move 2, 3, so they will always have the same amount of charge but without the signs. So that's one way to charge them, right? And the problem says I want to know how many electrons I need to remove. I need to move from this plate to that plate in order to get the electric field, right? So that means you're going to just do things backwards. You use the electric field to find the charge density needed on each plate and find the charge needed on each plate. And then you can find the number of electrons you're going to move from this plate to that plate, right? Because once you have the total charge, you divide that by the charge of each electron, right? Which is a constant. All right, so that's what we're going to do, right? You're going to first use this conclusion, this equation for the parallel plate and the definition of sigma E to find the charge, and then you don't stop there. If the problem says, okay, how much charge does each plate need to have, that's your answer. But if it asks you how many electrons you need to move from one plate to the other, there's one more step. Okay, so this question you can pause the video and then do the algebra and then compare your answer with mine. All right, so let's see. So in this case, if I put everything together, so I should get E equals Q over A times epsilon naught, right? And then you rearrange this equation. At the end, you should get Q equals E times epsilon naught and then times A, right? You put everything together. The A, remember, it's going to be 0.01 meter times 0.02 meters. Right? So that's the area, because you're given the length and width. And the electric field, that's the electric field you want. And then epsilon naught is constant, right? All right, so and then you put all the numbers in, you should get the charge. Okay, that's only the charge you need on each plate, right? Then how do you find the number of these electrons needed to move from one plate to, you're going to do the charge divided by the amount of charge each electron carries, right? So that's going to give you 2.21 times 10 to the 10. All right, so that's the number of electrons must be moved from the first plate to the second plate. So in order to charge them with the same amount of charge, right, opposite signs. All right, so that's how we use this this conclusion for parallel plate capacitors. This is a very useful conclusion. We're gonna see parallel plates capacitors a lot, okay? Because as we can see, okay. So now let's take a look at the motion of charged particles in parallel plate capacitors, right? And that's going to be the simplest case. Because say if I have a positive plate, okay, a negative plate. Of course, the electric field I know now, okay, very uniform between them, okay, very nice, the perfect electric field I want. Now, say if I place a charge, okay, charged particle, elementary particle, proton, electron, or helium, ion, okay, things like that. So say place a positive charge here. Okay, of course the positive charge is going to feel a force. How do I find the force? That's the theory we learned, right? And that's why we spend a lot of time finding the theory for electric field, because once you have the electric field, finding the force is very easy, right? Now if I set up a uniform electric field, okay, everything's going to become easy, right? So this guy is going to feel a force. The magnitude is going to be product of these two numbers, okay? So if this guy is a charged particle, the charge is going to be this constant. And electric field, if I use parallel plate capacitors, electric field is going to be constant, right? Because that's why we are interested in parallel plate capacitors. So that means the force on this guy is going to be a constant as well, right? And in this case, this guy is going to feel a constant force to the right, right? So a constant force on an object, and as I said, right, at the very beginning of this this class, the gravity of these charged particles, you don't need to worry about them if there's an electric force on it, because that's going to be totally negligible, right? Because this guy is going to be like much larger, it's huge to the gravity of this guy. So you don't need to worry about the gravity of these charged particles. Now this guy has a force constant on it, so the acceleration is going to be constant, because that's the only force, so the net force is going to be constant, right? So that's what we learned in physics 1, Newton's second law, right? Even if you tell me you have already forgot what we learned in physics 1, F equals ma, okay? That's going to be something you're going to remember for the rest of your life, right? Okay? So if the net force on an object, doesn't matter what object it is, right? What this force is. The net force is constant, acceleration is constant. Constant acceleration motion, that's the first theory we learn in mechanics, right? You can always use kinematic equations to predict the motion of this object, okay? So that's the simplest case, okay? So we can go ahead and use this theory. So these are the notations we used in physics 1. So these three equations, they call kinematic equations, right? So that means we can still use this theory in this part if the particle, elementary particle, the charged particle, is moving in a uniform electric field. Okay, so that's why we are interested in parallel plate capacitors. Right? I make sure the electric field is very easy, very simple, and then I can use a very simple theory I learned in mechanics, okay? Apply that theory to these elementary particles, right? Because this theory, they're still true, right? Newton's law, they're still true in, with these fundamental particles, all right? So, and then you see everything's going to be the same. Everything's going to be the same. All you need to do is just if you want to predict the motion, well, use Newton's second law to find acceleration, then use kinematic equations to predict the velocity, the position, right, or even the time, okay, if there's one particle moving in a uniform electric field, okay? So that's what we want to practice next, okay? That's what we want to practice next. All right, so this thing, let's take a look at this question. Slide 15. Now we have two electrodes, 7 centimeters times 2 centimeters. Okay, so that's going to tell us the area. They are spaced 5 millimeter apart, so very, very close. Okay, so actually when you work with these fundamental elementary particles, you don't need to make a very big gap, because we're going to see that even if it's 5 millimeter, you can accelerate them to a very large speed. So when you deal with these guys, okay, all these numbers can be very small, all the dimensions can be very small. That's why the conclusions are useful, right? When the two plates are very, very close, okay, but they're still a very big size for these elementary particles, okay? So 5 millimeters apart, so each electrode has been charged with 65 nanoCoulombs, okay? So this guy say 65 nanoCoulombs, negative 65 nanoCoulombs, right? So each is 7 centimeters times 2 centimeters each plate. A proton is released from rest at the surface of the positive plate. What is the speed of the proton when it reaches negative plate? Okay, so now we're going to release a positive proton, right? Proton is positive, so of course it's going to feel force to the right. So if you release it here, it's going to feel force to the right, force constant, acceleration constant, so it's going to be moving toward the negative plate, and then it's going to get faster and faster because it's accelerating, right? So we want to predict what? We want to predict the speed when it reaches the negative plate, right? Of course, at the end, it's going to reach the negative plate. We want to find the speed here. Okay, in order to find the speed, because this is constant acceleration motion, I can use kinematic equations. Okay, so all I need to do is that I can use this Newton's second law to find the net force, and I use this to find the net force, because the only force on it is the electric force. So that's going to be the net force on this proton. And then use Newton's second law to find the acceleration. Okay? So once you find the acceleration, you can pick one of these equations to find the velocity, right? And the easiest one is going to be the first one, because once you have the acceleration, no, because you don't have the time, right? So this is not going to be the easiest one. The easiest one is going to be the third one, because you have the distance between them, right? The distance between them is 5 millimeters. So the proton is going to travel 5 millimeters to reach the negative plate. So that's going to be the xf minus xi, right? So the third equation is going to be easiest, because the initial velocity is 0, right? You're released from rest. Acceleration you calculate from Newton's second law. You go ahead and solve this equation. Okay, so a few steps. Okay, only this is new. Only this is the new, right? But the rest is what we learn in physics 1, in mechanics. Okay, you also, of course, you need the charge of an electron, and this, and the mass of the proton. The mass of a proton, constant, and then you can go ahead and find the speed of the proton. Okay, pause the video, do the algebra, see if you can get the right answer. All right, so let's see. The acceleration, so let's see the numbers I got. You're going to do the net force, right? In this case, it's just the electric force, which is going to be charge times the electric field. Electric field is not given, so you're going to find the electric field. Proton, right? So, and then the electric field, you're going to use the theory for the parallel plate capacitors, right? So it's going to be Q over A. Okay, no, it's going to be sigma E over epsilon naught, and sigma E is going to be charge over area divided by epsilon naught, right? Epsilon naught is also a constant. Right? So charge is given, again, you don't need to multiply the charge divided by 2, right? Everything has been already considered when this equation was derived, so you don't need to do that. So you just use the 65 nanoCoulombs divided by the area. That's going to be the surface charge density, right? Of course, everything else are units. Divided by epsilon naught. So this number, this is what I got. So that's the electric field between these two plates, right? Plug it into this equation, okay? You can find the acceleration, okay? And once you find the acceleration, you can do this. Equals 0 squared plus 2, and then this is going to be 5 times 10 to the negative third meter, right? All right, so at the end, what are you going to get is going to be this is what I got, 2.24 times 10 to the 6th meters per second squared. All right, so this is the velocity. This is the velocity of this proton when it reaches the negative plate. Okay, so it's still Newton's second law and the kinematic equations. The only new theory is this, right? You find this electric field and then plug it into the Newton's second law, and the net force is just going to be the electric force, okay, in this case. All right, so okay, so let's see. Now that's just one-dimensional motion, right? So let's take a look at when this charge has an initial velocity, okay? If it has an initial velocity, and then the initial velocity, it's not in the excuse me, in the direction of the electric force or electric field, okay? So it's not going to be moving in a straight line, okay? So it's not going to be moving in a straight line, but all the theories, okay, the theory is still going to be the same, okay? So that's what we want to practice next. So take a look at this question. An electron gun creates a beam of electrons moving horizontally with the speed 1.5 times 10 to the 7th meters per second, right? Now the electrons, they're going to enter 2 centimeter long gap, okay, between two parallel electrodes, where the electric field is 5 times 10 to the 4th newtons per coulomb up, okay. So this is the electric, these are the plates, okay. Now the top plate is negative, positive plate, the bottom plate is positive, okay. Of course, the electric field is going to be up, right? Always from positive to negative. So I know how to draw the electric field, even if the problem doesn't tell me. And the electric field is going to be very uniform between these two plates, right? The electric field, the problem already tells me 5 times 10 to the 4th. Okay? Now, some electrons are going to enter this region, right? So these electrons, so let's just draw one. So they already carry initial velocity. So this initial velocity is going to be 1.5 times 10 to the 7th meters per second, already very large, right? So if that's the case, so this is the electric field. Electron enters the electric field. Of course, it's going to feel an electric force, right? So the force, what is the direction of the force? Again, use this theory. Right? Magnitude, multiply them together. Direction, take a look at the sign of the charge. Right? Now the charge is negative, so it's going to feel a force opposite to the field. Right? So this guy is going to feel a force down. So electron feels the force down, right? But it has an initial velocity in this direction, so it feels the force constant, always pulls it down, right? So it's going to be moving like this. So it's going to be moving in a parabola, not in a straight line, right? Does this remind you a motion we learned in physics 1? Of course, right? Something has a horizontal initial velocity, but there's a constant force pulling it down, right? What is that motion? Projectile motion, horizontal projectile motion, right? It's pretty much like this, right? You throw this guy horizontally, then it's going to move in a parabola, right? So this is exactly projectile motion, right? So this force, now it's not gravity. As I said, gravity, you don't need to consider that, right? Because gravity compared to this electric force is going to be negligible. So this guy is pretty much like the gravity you create, okay, using this electric field, okay? So the electron feels always a force down in this problem, right? But it has an initial velocity or horizontal. So it's a horizontal projectile motion. Okay, so we're just going to use the theory we learned for projectile motion in physics 1 and apply that here, right? What did we learn about projectile motion? X and Y totally independent, right? You break it into X and Y, then you do everything in X direction, you do everything in Y direction. They're totally independent. You don't get them mixed up. The only thing you can use for both directions is time, right? They share the same time, but other than that, velocity, acceleration, forces, totally different. You should definitely separate them, okay? And then the theory for the equations we're going to use in each direction is still going to be these three equations, right? You just like, these are the equations using X direction, you use them in Y direction. Well, if you like, you just replace all the X's with Y's, right? But X and Y, you know, they're totally arbitrary, right? All right? Is it wrong to call vertical direction X or Z or A or B? No, right? Okay? So the same theory, kinematic equations in both X and Y directions. Now, in X direction, so again, as I said, velocities, accelerations, forces, they're totally different, independent in each direction. You don't get them mixed up. So this guy has an initial velocity in X direction, if you still call this X direction, right? So this is actually telling you this is Vx, right? Then what is the initial velocity in Y direction in this problem? And this problem is going to be 0, right? Initially, it doesn't have any velocity in Y direction, okay? So the Y direction, you're going to write a Vyi equals 0. Okay, so now we have these two initial velocities. Okay, so these are the numbers you can plug in this kinematic equation. Now, what about the acceleration, right? You also need the acceleration, okay, and also time, right? The acceleration, so then you would have you would have to use the Newton second to find acceleration, right? So in this problem, because the force is only in Y direction, right? So the AY is going to be this, right? So AY, if you want to find AY, that's going to be the net force in Y direction over the mass of the electron. And in this case, the net force in Y direction is the electric force, right? And there's only one force in Y direction, because gravity, you can totally ignore them, okay? Totally negligible. So this is going to be the electric force on it. And then how do you find the electric force? That's going to be still charge times the electric field. And this problem is going to be easier than the previous one because the electric field is already given. You don't need to find the electric field, okay? So that's how you find the acceleration in Y direction. What about the acceleration in X direction? Is there any force in X direction? No, right? So this is exactly like horizontal projectile motion, X direction 0, because there's no force in X direction, right? So that's the initial velocities, that's the accelerations. Now let's see what we want to find. We want to find the first part, we want to find the velocity of the electrons when they leave the gap. So when they leave the gap, they're going to be moving this direction, right? They're going to be deflected. So they don't move in this direction anymore, right? How do you find this velocity? This is a vector. You should be careful, right? So all you can do is to find the components. So this is Vxf, this is Vyf. Then you can combine them to find this Vf, right? If this is Vf. So this is, then this Vf, so how do I describe this Vf? I'm going to use the magnitude and direction. Magnitude is going to be the length, and then direction you use an angle, right? So we have done that many times in physics 1, and also electric forces, and then electric field, right? Now we're just doing projectile motion, right? So all you need to do is just find these two components, Vxf and Vxy. Combine them to find Vf, okay? Vxf, easy. You don't even need to find that. What is Vxf? That's going to be the same, right? Because the initial velocity, in X direction, there's no acceleration. So there's no change in X direction. So at least this guy, I don't need to find it. So all I need to find is going to be Vyf And once I have that, I just do vector analysis, right? Because the magnitude is going to be x squared plus y squared and then square root. Direction, well, okay, pick a reference axis, okay? And then you can find an angle, okay? Then how do we find the VYF? That's going to be one of these equations, right? Kinematic equations. So in order to find the VYF, you're going to pick one, okay? So either the first one or the third one, because the second one doesn't give you VYF, right? So if I want to let's try the first one, because the first one looks easier than the second one. I would need a VYI, right? Everything is going to be replaced, every x is going to be replaced by y. VYI is 0, easy. Now I'm going to need the acceleration. Oh, that's how we find acceleration, right? I still use Newton's second law. I just need to find net force, the electric force on it, by using this new theory we learned in this part, right? What about time? The time, I don't have that, right? I don't have that. So either you find the time or you try a different equation, right? So if you don't want to find the time, you try this equation, let's see. Then you would need to, so Vy is still 0, Ay you can find it. But you're going to find the distance travels in y direction. The problem doesn't tell you, the problem didn't tell you, right? The distance it travels, right? You don't know the distance it travels in y direction, okay? So this one, you're still missing the distance traveled in y direction, okay? So there's no way you can get rid of either you find the time or you find this, right? So let's stick with the first equation. Let's find the time. If I want to find the time, as I said, in projectile motion, the only number you can use in both equations is going to be the time. Because in each direction it's going to travel the same time. It's one object moving, right? Of course, even if you break it into x and y, the time is the same. So I can actually find the time in x direction and then plug it into y direction, right? So that's always our strategy in physics 1, right? So in order to find the time, I'm going to switch to x direction because x direction is very easy, right? So x direction, if you still remember, if it's a projectile motion, the acceleration is 0 in x direction. The only useful equation is going to be the second one, right? Because if the ax is 0, the first equation is going to become Vxf equals Vxi, which you already know, right? Because the acceleration is 0. The velocity is always the same, right? So the first equation is not going to tell you any new information. And the third equation is going to tell you the same information if the acceleration is 0, right? This guy becomes 0. So it's still telling you the velocity stays constant. So if the acceleration is 0 in x direction, the only useful equation is going to be the second one, right? So okay, so that's going to be our strategy. I'm going to use this equation to find the time and then plug it into the first equation in y direction and find the final velocity in y direction. Then I can go ahead and find the final velocity, right? Because I already have the Vxf, all right? So let's see if I can find the time using this equation. Xf and Xi, okay? So in this problem, we already know that. So that's the 2 centimeter length, okay? So the length, so that's going to be the direction, the length it travels, right? Because it doesn't matter how much it travels in y direction. In x direction, it's going to pass this region, okay? So that means the length it travels in x direction is going to be 0.2 centimeter, okay? So 2 centimeters, yeah. Right? So that's going to be the xf, right? So xi is 0, xf is 2 centimeters, and Vxi we're given. Okay, so you can find time using this equation. Okay, so that's everything we're going to do. Okay, now you can pause the video, follow these steps, find the final velocity in y direction, and combine them to find the magnitude and the direction of this final velocity. Okay? All right, so let's see. First of all, the time I found, what are the numbers I found? The time I found is going to be, right, you're just going to do xf minus xi over Vxi. That's 1.33 times 10 to the negative 9 seconds. It's a very short time, right? Very short time. It's going to pass this region in very short time, of course, because it's carrying a very large speed. Now you need to find the VYY, but before that you need the AI acceleration y direction, right? So this number, it's going to be the electric field times the charge of an electron. Electron still carries this, right? And everything positive because I'm calculating the magnitude, the mass of the electron. Now the mass of the electron, okay, that's going to be, oh, that's mass proton. So mass of the electron is also constant. Okay, so mass of the electron, you plug in a charge of the electron is this. The electric field is given, right? So the acceleration you can find, this is going to be a very large acceleration. Okay, so that's the acceleration. And then you can go ahead and find the final velocity in y direction, right? Because the initial is 0, and then ay theta t, right? So you multiply these two numbers together, you would get this is 1.17 times 10 to the 7th meters per second. All right, then I'm going to combine them to find the magnitude and direction, right? So we have done that many times. So the magnitude VF is going to be x squared plus y squared, right, and then square root. So this is going to give me 1.90 times 10 to the 7 meters per second. All right, so that's the final velocity of this guy at this point. Now the direction, right? So again, if you want to use x-axis, use the reference axis. So I would just pick this angle, theta, right? So I would say this angle below positive x, right? Below positive x, right? So then this angle is going to be inverse tangent. In this case, y over x, right? Again, you draw it out. You know which one over which one. Okay, you don't need to remember these shortcuts. So this is going to give me 38 degrees. So 38 degrees below positive x, right? So that's how I'm going to describe the magnitude and direction of this final velocity. Okay, so this is exactly horizontal projectile motion. Now, let's take a look at the last part. We want to find the vertical displacement of the electrons when they leave the gap. Okay, so now we still need to find the displacement in y direction, which is going to be this distance, right? Which is going to be this distance. So that's just going to be YF, right? If you call YI, this is 0, right? So that's just going to be YF. Okay, so just need to find this YF. And this YF, which equation are going to use? Well, it's going to be either the second one or the third one. Right? Either one is going to help you find the YF, right? Because you already know we have already found everything in y direction. All right, so now you can pause the video, find this YF. All right, so the YF, say if I use the second equation, it's going to be yi 0, right? You can call this this is how you set up your origin. If this is how where you set up your origin, right? So this is y equals 0, this line. Vyi 0. Okay. Now 1/2 ay times theta t squared. Right? Ay we just found it. Oh, I just erased that. Okay. But then the theta t is the same, right? Ay, what we found is 8.78 times 10 to the 15th meters per second squared. Theta t is still the same, right? You plug all the numbers in, you would get 7.77 times 10 to the negative third meters. Okay, so that's about like 8 millimeters, okay? And of course the direction is down, it's not up, right? Because it's deflected down, the force is down. Electric field is up, force is down because it's a negative charge, right? And that's the original number, right? That's original, that's like 8 millimeters. That's usually the distance, okay? You're dealing with these elementary particles, okay? If you get like 7,000 meters, okay? Well, think about it, right? We are doing experiments with the electrons. You're not gonna have set up an experiment, the electron, like you're gonna need to set up the two plates like a few kilometers apart, okay? So that's going to be really hard. So that's one way to check if your answers make sense, okay? So this answer makes sense, like 8 millimeters, okay? So so let's see what we learned today. If there's a charged particle moving in a uniform electric field, okay, that's actually easy. We can use the theories we learned in Physics 1 to analyze the motion of a charged particle in a uniform electric field, because in that case it's just going to be a constant acceleration motion, okay? So it may move in a straight line if the velocity and the force and the field, they're along the same line. So it's pretty much, it's just going to become a one-dimensional motion, right, problem, okay? The only difference is the force. You may need to calculate that using the theory we learned in this part. But once you have the force, you can still do Newton's second law, you can still do kinematic equations because it's a constant acceleration motion, right? And if the velocity is not along the same line as the force, the electric field, so it may be moving in a parabola, right? It's not going to be moving in a straight line. In that case, it's pretty much like a projectile motion. Okay, you just need to break the motion into x and y directions, okay, and use the kinematic equations, Newton's second law, in x and y directions separately, right, independently. The only thing they have in common, the only thing they share is the time, right? That's the only number. You don't need to be very careful. You can use that in x, y directions. But other than that, don't get them mixed up, right? X values stay in x direction, y values stay in y direction. Okay, so that's what we did today. Now I'm gonna stop here for this video.